So welcome everyone. My two stories tonight actually are related, and if you've been paying attention to the news over the past month, you undoubtedly heard about the Nobel Prize in Physics that was announced on October 3rd, so just over 3 weeks ago, and they were given to Rainer Weiss, Barry Barish, and Kip Thorne. All three of whom are physicists, and they worked on detecting gravitational waves. And so in this case, the project that they're working on is called the Laser Interferometer Gravitational Wave Observatory, or LIGO, and we'll be talking about more about how LIGO exactly works. But there are two stations, one in Hanford, Washington, and the other one in Livingston, Louisiana. They're separated by about 3,000 kilometers. And so one of the goals of, the reason why you would want to do this is that as gravitational waves come in from deep space, you should see the same signal from both detectors, and we'll see how sensitive these devices are later on in the presentation as well. But what they detected just over 2 years ago was gravitational waves coming from a merger of two black holes. So we think these black holes were about 30 times the mass of our sun. One was slightly less than 30, the other one was slightly larger than 30. And this merger event took place more than 1 billion years ago. And over time, what happens is as these black holes orbit each other, they produce gravitational waves, and as the gravitational waves bleed energy from the system, they orbit closer and closer until they merge. And that final merger releases an enormous burst of gravitational waves, and that's what LIGO detected. And since then, LIGO has detected 3 additional black hole mergers. And this was such a momentous event that just 2 years later, the Nobel Prize in Physics was awarded to those 3 physicists. And even though, the Nobel Prize rules actually limit the prizes to people who are still alive and to no more than 3 scientists. And in fact, there are probably thousands of people who have worked on this project. And so even though the 3 awardees are definitely well suited to the award, you always hear griping among scientists. Not necessarily from the ones who feel like they've been gypped, but there is some concern about the fact that prizes like this don't give you the full picture of how science is done. And we'll see more examples of this too. All right, so first of all, let's talk about what gravitational waves are. And in order to do that, we have to go back 100 years to Albert Einstein and his theories of relativity. So just over 100 years ago, he released his special theory of relativity, and then also his general theory of relativity. And they basically revolutionized how people thought about time and space in the universe. And the way he did that was, and here I'll give you like a really short introduction to what general relativity means, is when we traditionally, classically, when we think and talk about space and time, we think of them as being these 2 separate, sort of amorphous, hard to define things having to do fundamental aspects of our universe. So space we think of as this 3-dimensional volume, like the room that we're in, that we can define by measurements like length, width, and height. And time is a little bit harder to explain, but one joke is that time is the universe's way of keeping everything from happening all at once. But normally we think of them as being separate. But Einstein realized that you can actually come up with a theory where space and time are actually inextricably linked together. So you can't really separate them, and you can't think of events as occurring at a single spot in space without also thinking about the additional dimension of time, what time that event occurred. And so from Einstein, we get this idea of space-time, this 4-dimensional construct. Next, Einstein realized that energy and matter were also equivalent. So this is another fundamental discovery by him. We think of energy to put things in motion, energy to heat something up, that is distinct from the matter that we're made up of. But Einstein, again, came up with this really radical idea that you can actually convert energy and to matter and vice versa. And this conversion is given by his very famous equation E equals mc squared, where the amount of matter times the speed of light squared gives you the amount of energy that is equivalent if you were to convert all that matter. And it turns out that there's an enormous amount of energy that is bundled up in the atoms and the matter that we're made up of. Now, the really important fundamental sort of connection that he made between space-time and this energy-matter equivalence was realizing that space-time can influence energy-matter, and then at the same time, energy and matter can influence space-time. And what we mean by that is that energy, the amount of matter and energy in the universe basically tells how space-time to curve or how it's distorted. So if there wasn't any matter or energy, space-time could be thought of as being flat with no geometric distortions. And then conversely, if you have space-time that's curved or distorted in some way, that actually changes the trajectory of matter and energy that travels through that space-time. So there's this effect that happens where one affects the other. And Einstein, in his theory of general relativity, came up with an equation to basically express there's a huge amount of mathematics that's bundled up into this very simple looking equation, but one side of it represents the amount of curvature of the space-time, and then the other represents the amount of matter and energy density that's causing that curvature. And so that's his famous field equation. And there are lots of examples that sort of demonstrate how this works. So the best one, or the easiest one to sort of think about, is this stretchy sheet where that represents the curved space-time, and you can roll marbles down it, and they represent particles of matter or energy that are flowing over the surface. And so they're, instead of moving in straight lines, they moved in curved lines because of the curvature of space-time. And there are examples out in our Space Odyssey exhibit and elsewhere in the museum where you can see this. And similarly, you can apply this to objects in our solar system, or really objects anywhere in the universe. So what we think of gravity, keeping things in orbit, can really properly, through relativity, be thought as massive objects curving space-time, and then that curvature causes those objects to orbit and to move in certain trajectories. So one of the other aspects of general relativity that Einstein thought about was he realized that gravitational waves also came out of his equations. And so in 1918, and there was, I think, an earlier paper as well, he published on what these basically the mathematics that predicted gravitational waves. And so this is right around 100 years ago, and Einstein actually didn't believe that we would ever have instrumentation that would be sensitive enough to detect gravitational waves, because these waves, which are basically a distortion of space-time caused by accelerating objects, are extremely weak. And you'll see the amount of work that it takes to detect them in just a minute. Now, the way gravitational waves work is here we're seeing an animation of gravitational wave that's propagating from left to right. But what happens is that the distortion that happens to objects or to space first occurs in one dimension, and then it occurs perpendicular to it in the other direction. So let's take a look at that again. So we'll see the gravitational wave propagate from left to right, and then if you look at the rings closely, you'll see they get stretched from side to side, and then they get stretched up and down. So basically, what gravitational waves do is they very subtly stretch space-time in this particular fashion. And so if you can detect that stretching, then you've made a detection of gravitational waves. There's actually a physicist, Joseph Weber, who at the University of Maryland back in 1969, 1970, actually had built early gravitational wave detectors. And what they were these giant aluminum drums. They're actually solid blocks of aluminum. And his idea was that if there was a cosmic event that created gravitational waves, the waves would pass through these giant blocks and they would set up oscillations in the aluminum. And if he had a bunch of them, he could basically have signals from all of them. And if they all detected the same sort of signals, you would have a positive detection. And the reason why he wanted to have multiple ones was so that thermal noise, heat, random heat fluctuations wouldn't cause false detections. And he reported detections of them right around the start of the 1970s, but other physicists were not able to replicate his work. And so unfortunately, he didn't really go anywhere with this initial study. And he believed that his method, if the National Science Foundation was to continue to fund him, would have allowed him to eventually perfect it and get it working. But the Nobel laureates all call him the father of gravitational wave physics, just because he was really the first person to try and do this. Now, what LIGO does, instead of having these large physical objects, is to use properties of light to make the detection. And so each LIGO observatory is actually something known as an interferometer, and it involves a laser source that sends off light into two different directions via a beam splitter. And so these are the long arms, which are up to, about 4 kilometers in length. And the light bounces off the mirrors at the end, and then they combine again via the beam splitter to the detector. And because of the wave properties of light, you can actually detect very minute changes in the distance that the lasers travel. Just like the animation that we saw about how the gravitational waves can actually cause these paths to distort or to shrink and grow again. And so the property of light that makes this possible is known as interference, and hence this is why it's called an interferometer. And the idea is that if you have two waves, and light is made up of electromagnetic waves, what can happen is that if the light waves are exactly aligned, so you have the peak of one wave matching the peak of the next wave, and the trough of the two waves matching, and if you combine them together, you basically get a wave with twice the amplitude, meaning twice the strength of the peaks and the troughs. Conversely, you have something, not surprisingly, called destructive interference, where the two waves are mismatched so that they're off by 180 degrees. And in this case, the peak is matched with the trough, and so they cancel out. And then the trough here is matched with the peak of the second wave, and they cancel out. And so when you combine them together, you basically get no signal whatsoever. So here is a video from a group that does science explanations. And what they're trying to do is show examples of interfering waves on a pond. So he's basically taken a tennis ball and bobbing it in the water, and you can see waves propagating out. And when he adds a second tennis ball, you can see the waves will start constructively and destructively interfering with each other. So the waves here will get back. Waves here are being constructively interfered, and then the waves here along the boundaries are being destructively interfered with. And so here is a really good example of how waves on the surface of a pond can give you destructive and constructive interference. Now, light waves are not the same as waves on a pond, but what happens is that for an interferometer, you have the laser sending off light to the two mirrors, and then they get recombined again. And the way the interferometer works, and so here we're going to follow along the waves. It bounces off that one mirror, and then the two go through the beam splitter. And the default position is for the two waves to destructively interfere. So the default case is to have these paths be exactly the same. And if a gravitational wave comes through, it's going to change these paths. And as the paths change, the light can go through constructive interference. And so you'll actually get a signal that a light detector can then detect. All right, so here is the history of gravitational wave observations or astronomy. Rainer Weiss, one of the Nobel laureates, actually conceived of using an interferometer back in 1967, where he had posed a problem to students. And in that problem, he came up with this idea of these interferometers along that kind of that L-shaped scheme that we saw earlier. And of course, I mentioned Joseph Weber, who tried to detect gravitational waves, starting in 1969, but his work wasn't replicated. Weiss started writing papers about what you would actually need to build his type of interferometer, and discussing the type of noise that you would have to reduce in order to actually make this work, because it turns out the amount of change in the path length of light from even massive sources like colliding black holes or merging black holes is about 1,000 times smaller than the width of a proton. Yeah. So you're talking about something, trying to measure a path length change as it's extremely tiny. And so you can imagine that someone walking along or the wind blowing against your building could probably cause fluctuations that could overwhelm your signal. So he first had to quantify all sources of noise that could hide the effect that they were looking for. In the 1970s, Kip Thorne started publishing papers on what sort of astronomical objects could actually emit gravitational waves that could be detected. So what's really exciting about LIGO and really any science that pushes the boundaries is that you have to invent new technologies in order to really make this happen. And I list a number of new technical achievements that they had to do, but I really only have time to talk about one, which is vibration isolation, meaning what can you do to basically isolate your mirrors so that vibrations from outside the experiment won't affect it. And so they do a lot of active vibration suppression, meaning most of those are relatively low frequency, and so they can actually have active feedback mechanisms to reduce those slower vibrations. But for the higher frequency vibrations, they actually use this really clever method of suspended mirrors, where instead of having mirrors that are placed on holders that are locked to the ground, they actually suspend the mirrors in the air. And what they do is they use a set of sort of pendulums. So the mirrors, they have multiple masses that are also suspended. And what happens is that if you have, let's say, a yo-yo that you're holding from the string, and if you were to shake it at high speed or at a high frequency, it turns out that if you by suspending these objects by fibers, you can actually reduce the amount of motions coming from these external sources of vibration. And so they end up having these 40 kilogram, so almost 100-pound masses to help suppress the vibrations. And they have these super thin silica or glass fibers that are thinner than a human hair. It turns out that glass fibers are actually really strong in this direction. You just don't want to flick them or hit them to the side, in which case they'll break. But they do this so that because these fibers don't expand under heat, so you don't want thermal changes. And what they found was that when LIGO initially opened, they were able to basically detect changes to the distance within the interferometer arms to within an order of about 10 to the minus 20 seconds. So that's how what fraction of the strain or the change in the length of the arms they could detect. But over time, they were able to improve the various technologies to suppress the different noises, and so currently it's down to here. And then the other lines here show some of the fundamental types of noise that would still be limiting if they try to go even deeper. And just to continue the history of this project, the federal government, through the National Science Foundation, decided to fund Weiss's work along with a competitor, Ronald Drever from Caltech. Drever later passed away, and so he wasn't one of the Nobel laureates because Nobel laureates have to be alive. And it took another 10 years or so before NSF and Congress was able to appropriate funding for the actual construction of the full LIGO observatory system. And then later on, Barry Barish joined the team and as kind of the project leader, and he helped with determining the final design of LIGO and getting the last bit of money to help fund it. And the collaboration eventually expanded so that it became a multinational collaboration, not just in the US. And today there are over 1,000 scientists working on the LIGO project. LIGO became operational right around the turn of the century. And here is just a map showing, again, the two observatories. And then the initial LIGO that went online wasn't sensitive enough to detect gravitational waves from colliding black holes, but it was a way for them to test out the technology and figure out what sorts of improvements needed to be made. And so that took a good part of the first decade of the 21st century. And then they went through the upgrades. And then finally, in September of 2015, they began their engineering run. And within weeks of that, they had their first detection. And then in fall of next year, they're expected to go through another series of upgrades again, where they could make the instrument perhaps 8 times more sensitive than it is currently. And so here is that detection of the first pair of colliding black holes. And so this measurement here at Hanford is basically the amount of the very small changes in the length of those interferometer arms that we're talking about. And then similarly, there's a similar detection in Livingston, but they were separated by a few microseconds apart because the two are separated geographically. And so here again is the detection, but broken out into frequency space. And so that is the kind of the science and the history behind the Nobel Prize in Physics for this year.